Welcome to part 2 of our chapter 2 test review. So number 7, we want to write that function as a product of linear factors, including the complex factors. Now, I'm going to let you use a graphing calculator on problems like this. So let's see if we can find any real zeros, preferably rational zeros. Okay, so looking at our graph, it looks like we might have zeros at 1 and 4. Looking at possible rational roots, 4 and 1 are both possible rational roots based on what we talked about on problem number 6. However, we need to make sure that 1 and 4 are roots. So 1 and 4 we just see from the graph. So what we'll do is we'll divide by x minus 1 and x minus 4 to see if they indeed are factors. Since we're dividing by a linear factor, we can go ahead and just use synthetic division. So we bring down the 1. 1 times 1 is 1. 1 times negative 4 is negative 4. 4 times 1 is 4. And 1 times negative 16 is negative 16. So we know that 1 is a 0, so x minus 1 is a factor. So we'll take our new coefficients and divide by x minus 4. So I bring down the 1. 1 times 4 is 4. 0 times 4 is 0. And 4 times 4 is 16. Good news, 4 is also a 0, so x minus 4 is a factor. So this is what I have so far. I know that I have x minus 1, x minus 4, and this factor over here is what I have left over from the division, which is going to be x squared plus 4. Now at this point, this is as much as we can factor with real numbers. However, we can find the complex zeros by setting that quadratic factor equal to 0. Now since we have no middle term, we can go ahead and solve by balancing. So x squared equals negative 4. Taking the square root of both sides. So x equals plus or minus 2i. So we have our factors from before, and their new factors will be x minus 2i and x plus 2i. Number 8 was similar to a problem I did in part 1, except now it looks like we have a complex root. Well, we know if there's one complex root, there is another. Remember that complex root come in conjugate pairs. So if 2i is a root, then we know that negative 2i is also a root. Just know those are complex conjugate pairs. So if 1 is a 0, x minus 1 is a factor. If negative 3 is a 0, x plus 3 is a factor. If 2i is a 0, negative 2i is a factor. And if negative 2i is a 0, x plus 2i is a factor. So I'm going to or FOIL those out and FOIL those out. So here I get x squared plus 3x minus x minus 3. Here I get x squared plus 2ix minus 2ix minus 4i squared. So simplifying, x squared plus 2x minus 3. Now notice over here that the 2ix and negative 2ix cancel out. I know that negative 4i squared is equal to negative 4 times negative 1, or positive 4. So this ends up being x squared plus 4. So to multiply them, one option is to make the rectangle. Go ahead and fill in the products. And then we'll write our answer, combining like terms. So x to the fourth. Notice that these two are not like, so plus 2x cubed. Now these two are like terms, so plus x squared plus 8x minus 12. Number 9. Could be one of the easier problems on this review. I did notice, however, that a lot of you wanted to multiply these together. Well, that's actually counterproductive because vertical asymptotes occur when the denominator is equal to 0. So if I wanted to solve this, I wouldn't want to FOIL it out because we want it in factored form. So we set each factor equal to 0. So the vertical asymptotes occur at x equals 2 and x equals negative 5. Okay, number 10, find the domain of that function. All polynomial functions have domains that are all real numbers. So, when we have a rational function, the only thing we need to worry about is when the denominator is equal to 0. So when is x squared plus 4 equal to 0? Well, if you try to solve it, you don't get real numbers. That means there are no holes in the domain. So the domain would be all real numbers. Or negative infinity to infinity. Okay, so on number 11, we're going to go ahead and graph the rational function. So the y-intercept is, remember, f of 0. Or 0. The x-intercept occurs when the numerator or top function is equal to 0. And we get x equals 0. Vertical asymptotes occur when the denominator is equal to 0. So we set the denominator equal to 0 and solve for x. This function has no horizontal asymptote. The degree of the top is bigger than the degree of the bottom. But since the degree of the top is exactly 1 more than the degree of the bottom, that means there is a slant asymptote. We're going to find that by dividing. Now, because we're dividing by a linear factor, we can use synthetic division. So put negative 2 on the outside, and then 1, 0, 0. Bring down the 1. 1 times negative 2 is negative 2. Negative 2 times negative 2 is 4. Excuse me there. So the quotient part is x minus 2, and that's going to be our slant asymptote. So there's my graph. There's my x and y intercept. My vertical asymptote is at x equals negative 2. And my slant asymptote is at y equals x minus 2. So there's the y-intercept of the slant asymptote. The slope is 1. Up 1 over 1. Do that a couple times. And then go ahead and draw in our slant asymptote. So we only have 1 point currently on our graph. So we need to find some more values. So for example, I might want to choose maybe x equals negative 1. And then over here, I might want to pick x equals negative 3. And I'm going to pick negative 5. So using the original equation, I'm going to go ahead and find my function values. So plug it in negative 1. I get 1. Plug it in negative 3. I get negative 9. Plug it in negative 5. I get negative 8. About negative 8.3. Negative 1, 1. So it looks like I can kind of draw that curve in there. Negative 3, negative 9. 1, 2, 3, 4, 5, 6, 7, 9. Negative 5, negative 8.3 is about right there. And I draw my curves in. And that's a good, decent sketch. Taking a look at the calculator, you can see that those indeed match. Okay, for the last one for review, we've got a rational function, 3x plus 1 all divided by x. So our y-intercept occurs at f of 0. Oh. I get 3 times 0 plus 1 over 0, which means there is no y-intercept. The x-intercepts happen when the top function is equal to 0. So we have an x-intercept at negative 1/3. So for vertical asymptotes, it's when the bottom function is equal to 0. So we get one at x equals 0. That explains why there is no y-intercept. For a horizontal asymptote, we notice that the degree of the top is equivalent to the degree of the bottom. So we take the ratio of their coefficients. 3 over 1 is 3. So y equals 3 is going to be our horizontal asymptote. So I've got a horizontal asymptote at x equals 0, or the y-axis, at y equals 3. My x-intercept at negative 1/3. And now that's the points I have. Okay, so over here, I've got a point down here. Maybe I should pick x equals negative 1. And over here, I'm going to pick probably positive 1. And I'm going to pick 3. So now I plug those values into my function. If I plug negative 1 in, so I get negative 3 plus 1, which is negative 2, divided by 1 is 2. When I plug 1 in there, excuse me, I get 4. And when I plug 3 in there, I get about 3.3. There's 1, 4. 3, about 3.3. So we can kind of see that, something like that up there. Here I've got negative 1, 2. And then kind of see what the graph's going to look like there. Now, if you're kind of unsure on how the curve will go, just pick another point for x and figure out f of x, and then hopefully you will find a nice curve. We take a look at our calculator's graph and we see that it matches. Thank you for watching.